Good afternoon, ladies and gentlemen. My name is Michal Šprlák and I am a researcher at the University of Newcastle. Together with Xinchan Han, we have been working on the rigorous forward modeling of the gravitational spectra with examples for the Moon. I would like to show you some of our findings and results. Our study is mainly based on the satellite mission GRAIL, which was mapping the lunar gravitational field in 2012. The twin satellites were orbiting the Moon only several tens of kilometers above its surface. This allowed scientists to determine the spherical harmonic coefficients up to the spherical harmonic degree and order 1500 that corresponds to the spatial resolution of 3.6 kilometers on the lunar equator. Believe it or not, the gravitational field of the Moon is the finest one among all planetary bodies. Besides GRAIL was realized more than 4 years ago, there are still many problems and challenges left. For example, we are working on an ARC discovery project. Our ultimate goal is to develop a global crustal model of the Moon. For this task, we also use methodology that is based on forward modeling. There are numerous forward modeling methods available, but they introduce crude postulates and approximations. In our study, however, we decided to exploit a rigorous approach as we suppose that this is the correct way for an accurate gravitational field modeling and realistic structural studies. Because we are talking about methodology, I need to introduce some mathematical aspects. By the rigorous approach, I mean the volume integration of the variable density ρ multiplied by the spherical harmonics y and m. The integral gives the spherical harmonic coefficients c and m, which refer to the sphere of radius capital R, enveloping all masses of the attracting body. From the theoretical point of view, this formula is as old as the Newton integral and the spherical harmonics. But from the practical point of view, its implementation is missing. Therefore, Xinchan himself closely looked at the equation, discretized it by tesseraoids, and coded it in Fortran. His effort resulted in an efficient program using the fast Fourier transform algorithm. Currently, the standard approach in geodesy and planetary sciences is the so-called finite amplitude method. It is a special case of the rigorous modeling with two assumptions. Firstly, the density ρ is constant. Secondly, the geometry of the attracting body is decomposed into the topographic sphere of radius d and topographic heights h. Then the spherical harmonic coefficients c and m are defined by a summation of the topographic coefficients h and mk, while the constant density is only a scaling factor. We can expect that the finite amplitude method is efficient because the topographic coefficients h and mk come from surface analysis of the powers of the topographic heights. Besides the efficiency, we need to be careful when selecting the radius of the topographic sphere and the maximum index of the summation. These parameters strongly affect the accuracy of the method. After the brief theoretical interlude, let's now move to the experimental part. We have performed many numerical experiments. Here, I restrict to only two of them. In both, we concentrated on the gravitational field inferred by the topographic or crustal masses of the Moon. In all cases, we determined the spherical harmonic coefficients up to degree and order 2519. So we are talking about an ultra-high expansion. The geometry of the Moon was defined by the LOLA digital elevation model, and we considered its different resolutions. Naturally, the minimum spacing corresponds to the harmonic degree and order 2519. We also assumed different values of density, from the uniform one of 2550 kg per meter cubed to a spatially variable. In the first experiment, we compared the performance of the rigorous approach with the finite amplitude method. We calculated the spherical harmonic coefficients by our newly developed program for the sampling of LOLA topography of 1/14, 1/28, and 1/56 degrees. In a similar way, we generated the gravitational spectrum by the finite amplitude method, which is implemented in the widely used package SH-Tools. In this case, the maximum power of the topographic heights was 20, and the radius of the topographic sphere was 1737.4 kilometers. The results of the comparison are depicted in the figure in terms of the square root of the degree variances. The solid blue line is the power of the signal by the rigorous approach. The black solid line is the power of coefficient differences between the reference signal and the finite amplitude method. It gives us confidence that the new program is really correct with no systematic errors. The dashed blue and dotted blue lines show that the precision of the rigorous approach is better for the final LOLA grids. This is logical as the discretization error is lower. In the second experiment, we compared three global crustal models of the Moon. The first one was defined by the constant density value of 2550 kg per meter cubed. The density, changing with radius, was assumed in the second model, while the third model considered spatially variable density. We computed the spherical harmonic coefficients as generated by the three crustal models by our program and evaluated the three gravitational field models in terms of correlation and admittance with respect to the Grail gravitational field model GL1500E. The correlation as a function of the spherical harmonic degree is depicted in the figure. The low correlation below degree 100 is caused by the geophysical phenomena in the lunar core and mantle, and above degree 700 by the noise of the Grail measurements. The correlation is nearly 1 between the degrees 100 and 700 and proves the perfect match between the Grail gravitational field and the one generated by the crustal models. The correlations of all three crusts are identical, and this is why you can see only one curve in the figure. We can resolve the three crusts when looking at the admittance which is another spectral characteristic. As already explained above, the degrees below 100 are dominated by the geophysical phenomena, while the noise dominates above degree 700. Focusing on the band between degrees 100 and 700, we can see the constant slope of the admittance for the homogeneous crust. We can also see that the admittances of the more complex crustal models are closer to unity. They are mutually shifted because of the different values of the mean density. Overall, we have a good indication that the crustal models with the radially stratified and the spatially variable density are more realistic as compared to the uniform one, because they explain the slope of the admittance. Finally, let's move to the conclusions. Within this contribution, I discussed the rigorous forward modeling. We have implemented the approach in the computer program, tested for the case of the lunar gravitational field, and also applied for the comparison of the three crustal models of the Moon. Among all results, our study shows that the rigorous modeling up to ultra-high spherical harmonic degrees and orders is possible and manageable, as we performed all of the computations on an ordinary computer. In this way, we completely denied the established opinion that the rigorous modeling is not applicable due to significant computational effort. In the end, I would like to say that I could not show you many interesting details, but I hope that you may eventually find them in the article, which is now in preparation. That is all from my side, and I would like to thank you for your attention.